In this video, we'll be talking about network theorems. Network theorems are established principles that are designed to ease up the analysis of sophisticated circuits like this one. We have 6 network theorems. We have the Kirchhoff's laws, superposition theorem, nodal analysis, mesh analysis, Thevenin and Norton's theorems. In this video, we'll be looking at Kirchhoff's laws and the procedures that we have to go through when we are applying Kirchhoff's laws for circuit analysis. Kirchhoff's current law states that the algebraic sum of currents entering a node equals 0. In essence, what we're trying to say is that if we take this node, for example, we have currents that are departing from the node and currents that are entering the node simultaneously. According to Kirchhoff's current law, we can say that the sum of current entering the node equals the sum of current leaving the node, or the total of all the currents equals 0. That is to say that if I1 is entering the node, we take that as positive. We can say I1 then plus I4, and those that are leaving the node, we take them as negative. Then we can say minus I2 minus I3 and minus I5. Then we can equate them to 0. So the total sum of all of them are equals to 0. That's what Kirchhoff's current law is saying. Then we can also restate Kirchhoff's current law as the sum of currents entering a circuit as I1 plus I4 equals the sum of currents leaving the circuit. That's I2 plus I3 plus I5. Kirchhoff's voltage law states that the algebraic sum of voltages in a loop is equals to 0. Kirchhoff's voltage law is trying to establish, in essence, here is that the sum of the voltages and voltage drops in a loop is equals to 0. Take, for example, this voltage. Since it's supplying power to the circuit, we take it as positive, and since this resistance is taking power from the circuit, we take the voltage drop across it as negative. Then we can say that V minus I1 R1 minus I2 R2 minus I3 R3 equals 0. That is what Kirchhoff's voltage law is trying to tell us. Another Kirchhoff's voltage and current law, we can extract a system of equations that will allow us to be able to analyze and determine any unknown in an electric circuit. Assigning polarities to voltage drops is easy when you have one power source in the circuit. What you just do is you look at the resistance and you say, oh, this is closer to the positive terminal of the power source. You give this positive. This is closer to the negative terminal. You give this negative. This terminal is closer to the negative terminal. Negative. This terminal is closer to the positive terminal. Positive. This terminal is closer to the positive terminal. Positive. And you make this negative. Then you look at this one, it's closer to the negative. Then you make this one positive. This will be positive. Then you get this one positive and negative. And that's how you assign it when you have only one power source in the circuit. If you have more than one power source, however, it's still easy. You just ignore these other power sources and you just pick one and ignore other power sources. So let's assume you pick this one and ignore the rest, and then you use that to assign your polarities. Then this one will be positive, negative, positive, negative, positive, negative, positive, negative, negative, positive. This would be positive, negative. This would be negative, positive. This would be negative, positive, this will be negative, and this one will be positive. And then you've assigned polarities to all your voltage drops. The next thing to do is to assign current to branches that have no current. So this branch, for example, would be branch I1. This branch will have a current of, say, I3. I2 has already been assigned to this one. This branch should have I4. This branch would have I5. Notice the direction of the current. It flows through the voltage drops from positive to negative. This one would be I6. This one would be I7. This one would be I8. This one would be I9. I believe we have assigned current to every branch. We can then proceed to the next step. It would be to write KCL equation and all the relevant nodes. Take this node for example. We have current I1 entering the node, current I2 and I4 leaving the node. So we can say that I1 equals I2 plus I4. We can call that our first equation. We can then move on to the next node and say, okay, I2 is entering the node, then I3 and I7 are leaving, equals I3 plus I7. Take this node for example. You can come here and say, okay, I7 is entering the node, I9 is entering the node, I6 is entering the node, and I5 is leaving. So we can say I7 plus I6 plus I9 equals I5. And that is how you write KCL equations, and you keep writing them until you are done with all the relevant nodes. Done writing the KCL equations. The next thing you want to do is to write the KVL equations, Kirchhoff voltage law equations. In order to do that, you pick the loops you want to write. Let's say this is your first loop, your second loop, this is your third loop. And say this first loop you want to write the Kirchhoff's voltage law equation in that loop. So you look at the loop alone, then you start from a node in the loop. So as you move through the node, the polarity you hit first, you write it. That will be positive. So you write plus. Then you write the current I1 R1. That is the voltage drop. Then you come down and you hit another positive. So that will be plus I4 R2. That would be the voltage drop. Then you keep moving, then you hit a negative. Let's call this voltage V. Then you have minus V. And you equate it to 0. That is how you write the Kirchhoff's voltage law for this loop. Then if you are going to this loop, you start from here and you move, you hit a positive. So that will be plus. Then the voltage will be I2 R3. I2 R3. Then you come, then you hit another positive plus I7 R5. I7 R5. Then you come and you hit this. That will be plus I5 R4. Then you come and you hit this. Then you have a minus. Minus I4 R2 equals 0. And that is the KVL equation for this loop. One thing you should never make the mistake of doing is, if a loop contains a current source like this loop should not be used to write a KVL equation. Time you're done writing the KVL and the KCL equations in the circuit, you would have enough equations that you can solve simultaneously to determine the individual currents flowing through each resistor. From there, you'll be able to calculate the voltage drop across each resistor and the power dissipated in each resistor.